Hi, hi everyone. We've been talking about the benefits of randomized algorithm. Um, First benefit is they're often highly efficient. Second benefit is they're often much simpler than a deterministic algorithm. Even in those cases where we have a deterministic algorithm, not to mention those cases where we don't have a efficient deterministic algorithm. And the third reason is that in terms of reliability, randomized algorithms, although they can make errors, if the error probability is small enough, then they are as good as a deterministic algorithm, because even deterministic algorithms can make errors, not because of the algorithm is erroneous, but because of um, radiation that changes bits in the hardware. And this is nothing that an algorithm can fix. So even a deterministic algorithm is subject to such errors. And if we have a randomized algorithm whose error probability we can control in our analysis and make it, let's say, less than 2 to the minus 100, then for all practicable purposes, this is as good as a deterministic algorithm. So 3 reasons why a randomized algorithm is interest, is relevant. And we will use this yardstick of error probability 2 to the minus 100 in the rest of this chapter. So this is our goal, to design probabilistic algorithms whose error probability is less than 2 to the minus 100, roughly. Okay, and we've uh, learned about 2 popular classes of randomized algorithms, Las Vegas and Monte Carlo algorithms. And I've asked you to kind of recapitulate from discrete math courses about these notions from probability theory. Well, what is a random variable? What is independence? What is the expected value? What is space theorem on conditional probability? And Las Vegas algorithm is an algorithm where the result is always correct, but its running time is a random variable. So we only can talk about expected running time. We can also talk about the variance of the running time, but we will not be able to talk about the worst case running time that could be very large. Whereas Monte Carlo algorithm takes a different view on this trade-off between correctness and running time. Namely, in a Monte Carlo algorithm, the answer will only be probably correct, in the sense that we have made formal with error analysis, one-sided, two-sided errors. On the other hand, in a Monte Carlo algorithm, we have a guaranteed runtime. And quicksort is an example of a Las Vegas algorithm where the result is always correct. It's always a sorted sequence, but the running time in the worst case could be still quadratic. Quicksort with randomized pivot search. Uh, Running time could still be quadratic, as bad as bubble sort. Only in the expected case, with actually very high concentration, so small variance, a randomized quicksort has running time n log n. So here's another example problem in algorithm, namely primality testing. Primality testing is the problem: given a natural number, tell me whether this number is a prime number or not. So this is a decision problem, and more general decision problems are problems where we have an input, in this case, let's say a natural number, and the output is only supposed to be yes or no. So not function problem where the output could be, for instance, some number, some proper factor of the input. That would be the factorization problem, which is subtly different from the decision problem. And So in a decision problem for primality testing, the set L, subset of natural numbers we're talking about, is a set of prime numbers. So whether the given input X belongs to this set or not is the same as saying whether the given natural number is a prime number or not. And this is, for instance, implemented in computer algebra systems with the is_prime function. And we're interested in ways how this is_prime function is implemented, that is in algorithms that test whether a given natural number is a prime number or not. Now, a simple deterministic algorithm would test all possible candidate factors of X. That is, check whether 2 is a divisor of X, 3 is a divisor of X, 4. Well, we already know that 2 is not a divisor of X, so we don't need to test 4. That's a zero of Eratosthenes approach to primality testing. But asymptotically, actually, it doesn't make much difference whether we test every number between 2 and X minus 1, or actually every number between 2 and the square root of X suffices to test for being a possible factor divisor of X. If there's no divisor of X less than the square root of prime, then there's also no proper divisor of X greater than the square root of prime, because to every divisor there's a co-divisor that would then be larger than, that would then be smaller than square root of prime. So how many divisors are to be tested? Roughly O of X or O of square root of X. But remember that we want to measure the running time not in dependence on the value X, but it depends on the length of the argument X. The binary length of X is roughly log X, and this is what we usually denote by N, so that the naive algorithm sieve of Eratosthenes, for instance, is actually an exponential time algorithm, right? Its running time depends exponentially on the length, polynomially on the value, but exponentially on the length. So that's that's why people have looked for more efficient algorithms, and so more efficient algorithm actually has been found, like in 2002, 2003, Agrawal, Kayal, and Saxena found a deterministic test whose running time is roughly n to the 7 or n to the 6. There were some improvements. So that is a polynomial time algorithm, right? It's a polynomial in n, where n denotes the length of x. So n is the binary logarithm roughly of x. But as I said earlier, such deterministic algorithms tend to be very complicated. And also the running time here, n to the 7, well, it is polynomial, but it's a very large polynomial of degree 7. So this is not really practical algorithm. On the other hand, randomized tests tend to be very simple algorithms and practically efficient. So let's start looking for a randomized test for primality. And a naive idea could be to maybe just guess a prime factor of X, right? So that let's analyze that naive algorithm, guess and verify candidate proper factor of X. What is the probability that this algorithm makes an error? Okay, so in order, let's say the input is not a prime number. Let's say the input is actually the product of two primes, right? So consider this example input. Then in order for our algorithm to give the correct answer, in order for our randomized algorithm, the naive algorithm, to detect that this is a not a prime number, that this is a composite number, the algorithm must guess one of the two factors, one of the two large primes, right? If the algorithm guesses any other number, then this other number will not be a divisor, and therefore the algorithm will erroneously claim that the input number is a prime number because it has not guessed the right proper factor. So this is very unlikely actually that the algorithm guesses one of the two large primes because there are only two possible correct guesses, either of the two large primes. So the probability to guess one of the two large prime factors is roughly 2 divided by square root of x. There's a typo here. Square root of x, because one of the large prime factors will be less than square root of x. So that means the error probability is very large. And as we will see on the next slide, although we can amplify that reliability, we can decrease the error probability, still this is going to be after amplification, so after turning this into a bounded error algorithm, it will be an exponential time algorithm. So basically as bad as the sieve of Eratosthenes, which means that the naive algorithm is not a good algorithm, even in the randomized sense. So let's look at more sophisticated randomized primality test algorithms. But before that, let's briefly recall the notions of complexity for such randomized algorithms. So you might say that our X here, the product of two large primes, that's an exceptional case, right? Um, how about the typical, the average number? But there's a simple algorithm that tells whether, on average, correctly whether a given number is a prime number, namely to just say, no, it's not, it's a composite number. That algorithm is correct on average. Why is it correct on average? Because most numbers are composite. Actually, the prime number theorem says that only roughly every log nth number, a log x number is a prime number. So there are very few prime numbers. So an algorithm that ignores its input and just says the given number is the composite number will be correct on average. And you will see that this is an unreasonable algorithm. So that's why average case analysis in this case is an unreasonable way of analyzing. This is why we analyze our naive algorithm in the worst case. And the worst case is indeed where the input is a product of only two primes, so that the algorithm, in order to detect that this is a composite number, must guess at least one of the two primes, which is very unlikely. So that means we should look for more sophisticated randomized algorithms. And actually, there's a very famous such algorithm, which is called the Miller-Rabin test and Miller-Rabin. And this test is actually underlying the is prime implementation in many computer algebra systems. So let us look at this test. Test is the following. So input is x as usual, natural number. And this test will guess another natural number between 2 and x, strictly between 1 and x. And let's call this number a. And it's easy to guess such a number. Just sample such a number, maybe bitwise, using coin flips to guess the first bit of a, second bit of a, and so on. And then let's decompose x minus 1, the input, minus 1, into its even part and its odd part. So the even part means we look at how many powers of 2 divide x minus 1 and denote e, the number of these powers of 2. And the rest, which is not divisible by 2 anymore, which is an odd number, that we will denote by D. So this is the decomposition of x minus 1 into its even and odd part. And we look at the following logical property, denoted star here, whether the guess number A when raised to the dth power is or is not congruent to 1 modulo x, right? So you know modular arithmetic from discrete mathematics. So that's the first property. And the second property, whether A raised to the d times 2 to the r's power is or is not congruent to -1 modulo x for all natural numbers are strictly less than e. And observe that this testing whether this property holds, this is a purely mathematical property, but whether testing whether this property holds can be done efficiently, right? So how can this be done efficiently? Raising the guess number A to the dth power, that can be done using repeated squaring. Remember when we talked about the squaring problem at the very beginning of our lecture? So that only takes log d multiplications, remember? Actually, every multiplication will be executed modulo x. This prevents the number from becoming very large, right? So raising a number to the dth power could result in a very large number, but we will do this, all of this modulo x, and therefore the number will remain small, bounded by x. And similar here, we can calculate this powers efficiently using repeated squaring and then check whether it's congruent to -1 or not. So this is a very efficient algorithm. And the mathematical theorem says if this property holds, then x is a composite number. Second. So that's a theorem from a number theory. We're not going to prove that theorem, but we're just going to use it in the design of the Miller-Rabin test, which says if this property holds, then we can correctly claim that x is a composite number. It's not a prime number, which means that this test is a one-sided, is a test which makes an error. What does it mean it makes an error? Namely, if this property does not hold, then the test will say that x is a prime number. And this is not covered by the mathematical theorem. The theorem says only one direction. If property star holds, then x is composite, but it does not say the other direction. If x is composite, then this property does hold. That's wrong. So let's look at this mathematical theorem. If the property star, that should be a star, if property star holds, then x is composite, but not necessarily vice versa, which means that this test is a test with one-sided error. Whenever the test says the number is composite, then it is correct. But when the test says that the number is a prime number, that might be wrong. And so we're interested in analyzing the error probability of that test, the probability of false positive, the probability that the test says the number is prime number, although actually it's not. And this probability is covered by the second part of our theorem, which says if x actually is composite, then 1/4 roughly of all possible guesses A satisfy the property star. Or put differently, if the number is composite, then the probability that the algorithm correctly identifies it as composite is at least 25%, or the other way around. The probability for the algorithm to make an error is therefore at most 75%. Okay, at most 3/4. We're not going to prove that theorem. That's just that's a purely mathematical theorem in number theory. But you see how this theorem provides the rigorous analysis of the randomized test. First, the complexity, the cost we have analyzed, right? We've seen that this can all be performed in polynomial time by with this repeated squaring, right? And we've analyzed the error probability. We've seen that this is a one-sided test, and we've seen that the error probability, the probability for this test to wrongly say that the number is a prime number is at most 75%. Now, what if this error probability, if we want more reliability, right? So 75% error, that's pretty large, right? Would you trust someone who lies 3 out of 4 times? That's what this test says, right? 3 out of 4 times, the answer could be wrong. Only 1 out of 4 times, the answer could be right. But we have learned about this technique called probability amplification for one-sided tests. So we've distinguished between the two types of one-sided error, false positives and false negatives. And whenever we have a test with one-sided error whose probability is less than 1, in our example, the error probability was 75%, which is less than 1. So then we can amplify the reliability by repeating this one-sided test, let's say k times, and report that this number is a prime number only if all executions of the test say it's a prime number. And each execution may err with probability 75%, but all k of them to err with probability 75%, this probability is 75% to the kth power. And this is a much, much smaller probability. So here's a question for you. With the Miller-Rabin test, error probability 75%, how often should we repeat that test to achieve our goal reliability of 2 to the minus 100? So my question is, what is k? So if we take k equals 300, that suffices, right? Does it make sense? Or you can do the calculation with your calculator. Maybe 250 or something also suffices. Anyway, so 300 repetitions for sure guarantee that the Miller-Rabin test has our reliability of 2 to the minus 100, which is for all practical purpose as good as a deterministic algorithm. Or more general, if we have an here's another example. What if the error probability is much, much closer to 1? Let's say 99%, right? In this case, if we repeat this algorithm 70 times, then the error probability will have dropped below 1/2. And if we then do that 100 times, then we're below 2 to the minus 100. So repeating it 7,000 times, even in this case, look at this. I mean, the error probability is basically incredible, right? Would you trust anyone who lies 99% of the times? But still, if we have a one-sided error, then we can amplify that to get the error probability as low as we want, 2 to the minus 100. So this is about one-sided tests, right? And there was a question, right? Robert asked, can we get some example of running Miller-Rabin test on some prime and composite number? Actually, that's a great suggestion for a programming assignment. Yes. Okay, thanks, Robert. We'll consider that. Right, but returning to errors and error amplification, that was a case of one-sided error, which is easy to amplify just by repeating it, because here we build on the promise that the test only makes one-sided error. So by repeating the test and looking at all answers, if any answer deviates, then we know that this deviation will give the right answer. However, if we have an algorithm test with two-sided error, then the amplification is a little bit more subtle. Well, more subtle to analyze because again, the amplification algorithm is easy. Again, we're going to repeat the algorithms, let's say k times, and then just report the majority answer, right? And what is the probability of the majority to be right or wrong? Um, in this case, let's suppose the original test has error probability less than 50%. Again, if the error probability is equal to 50%, any algorithm can achieve that easily just by flipping a coin without actually looking at the input. Then the error probability is 50%, right? That's not a sensible algorithm, and there's no way to amplify the reliability of this nonsensical algorithm that only flips a coin without even looking at the input. However, the error probability is strictly less than 50%, then this amplification works, and the analysis is based on Hoeffding's inequality. And understand that this inequality is a little bit complicated to understand. So let's repeat more closely how Hoeffding's inequality can be used to analyze the error probability. We're not going to prove Hoeffding's inequality, we're just going to apply it. So let's look at Hoeffding's inequality again. Hoeffding says if we have independent random variables whose values are bounded between 0 and 1, then the probability that the average, right, so x bar denotes the average, right, of these random variables, that the average exceeds the expectation, the expected value of the average by t, where t is an arbitrary positive number. This probability is very small. So let me explain the intuition behind this inequality. So intuitively, if we have a random variable, then we kind of expect its output, its result, to be the expected value, right? You see the pun? We expect the value to be equal or at least close to its expected value. Or put differently, we expect that it is unlikely for its value to exceed, to significantly deviate from the expected value. And this is exactly what this inequality says. It says that the actual value of this new random variable x bar differs from its expected value by at least t. This is what this expression says. And Hoeffding says this probability is indeed very small, exponentially small, right? E to then some negative number, that's exponentially. Exponentially small, where the exponent depends on k, we'll return that in a minute, and t saying how far the actual value deviates from the expectation. Now, in general, when x is an arbitrary random variable, this is very wrong, right? You can easily construct random variables that deviate from its expected value most of the time, right? So just consider random variable that, yeah, anyway. But the point is here, the hypothesis is that these are independent random variables, and the variable we are looking at, x bar, is the average of independent random variables with bounded values. And under this, hypothesis, that's where Hafting says it's very unlikely that the actual value deviates from the expected value by more than t. And we're going to apply this in order to analyze our meta algorithm B prime, our reliability amplification. Namely, we're going to consider xn to be the random variable that the nth execution of our algorithm B errors. Okay, so whether the nth execution of our algorithm B errors or not, that's a random variable, and it's a 0, 1 Bernoulli random variable, right? 1 if it errors, 0 if it does not err. So that this means this is the expected value, the expectation of our meta algorithm B prime to error, right? This is the expected case, and indeed the hypothesis of Hafting's inequality is satisfied because the different executions of our algorithm B are by construction independent. The next execution uses a different set of coin flips in order to arrive at the probabilistic answer. And also we're going to choose a particular value for t, and we're going to choose 1/2 minus p. Now, since p is supposed to be less than 1/2, that means 1/2 minus p is indeed a positive real number. So the hypothesis of the Hafting's inequality are satisfied. We may apply the inequality to get what? Well, as I said, x bar in our application means the the number of times, the average number of times that the repeated execution of B gives the wrong answer. And what's the right-hand side here? That's the expectation. What's the expectation of our random variable x bar? How often do we expect the repeated execution of B to fail? Well, we expect one execution to fail with probability P. So K executions are going to be expected to fail K times P times. But since this is the average, since we divide by K, that means the expected value of this random variable is also P again, right? So by linearity of expectation, this is just P, and T is 50% minus P, so that this right-hand side of the expression is actually just 50%, 1/2. So what we're talking about here is the probability that more or at least half of the executions give the wrong answer, right? This is what this condition says. And this is exactly the probability that our meta algorithm B prime fails. When more than half of the execution gives the wrong answer, that means the majority gives the wrong answer. This is precisely when our algorithm B prime gives the wrong answer. So that this here denotes the error probability of our algorithm B prime. And Hafting's inequality thus says, applied to this case, it says the probability of our amplified algorithm to fail is at most e to the minus 2 times k times t squared. Now, if you plug in t equals 1/2, this right-hand side expression is e to the minus k/2, roughly. Right? So t squared is then 1/4, cancel with this 2. So that's minus k/2. So that if we choose what? If we choose k, for instance, equal to 200, that means that the error probability has become smaller than 2 to the minus 100. That's our yardstick for being as reliable as a deterministic algorithm, right? So simply repeating and taking the majority also works in this case. We can amplify any algorithm whose error probability is just a little bit less than 1/2. Good. So here's another example. If the error probability is 1/3, then it suffices to repeat the algorithm 100 times in order to amplify its its reliability beyond the probability of any deterministic algorithm to fail due to radiation. Okay, and we've already talked about another randomized algorithm, namely a randomized algorithm for the polynomial identity test. So let me remind you, polynomial identity test. This can be considered as a variant or generalization of this parlor game 20 questions that we played last time, right? So I think of a number and you have to guess that number. And in order to guess that number, you can ask me questions, but at most 20 questions of the form, is the number you're thinking about greater or smaller than this something, okay? And after 20 questions, then you have to tell me the answer, which number I'm thinking about. And the version we're interested in here is the following. I'm thinking about a polynomial, some fixed polynomial unknown to you, but you can ask me questions about this polynomial. Namely, you can ask me a question about the values of this polynomial, and your goal is to determine whether the polynomial I'm thinking about is the zero polynomial or not. Zero polynomial means it is identically zero, and non-zero polynomial means there exists some argument for which the polynomial is not zero, or put differently, there exists some monomial which has a non-zero coefficient in its expansion. So the kind of question you're allowed to ask is, give me some argument, and then I will tell you the value of this polynomial. And you might be interested particularly in whether the value of this polynomial is zero or not. If it's not zero, then you immediately know that my polynomial is not the zero polynomial, right? But if the value is zero, then you cannot be sure, because maybe the argument x that you provided to me, that you've asked me for, could be a root of the polynomial, although my polynomial is not the zero polynomial in general. So that gives rise to the following generic black box polynomial test for my polynomial p. You fix a finite set, you sample, you guess a value from that set uniformly at random, and you ask me what is the value of my polynomial on this sample argument. And if the value I return is zero, then you say Martin's polynomial is the zero polynomial. Otherwise you say this is not the zeroth polynomial. So this is a simple, as usual with most of the randomized algorithms, it's a simple algorithm. And it's an algorithm which makes only one-sided errors, right? Namely, if the algorithm says this is not the zero polynomial, that means it is not the zero polynomial, because it means you have sampled, you have guessed, you have found an argument where the value of my polynomial is non-zero. So when we analyze this algorithm, as we're going to do in a minute, we're interested in the probability of false positive, namely when the test says it is a zero polynomial, but actually it's not. Put differently, we need to analyze the probability that the sampled argument x happens to be a root of a non-zero polynomial. And this probability is easy to analyze if we have a promise on the degree of the polynomial and if it's a univariate polynomial. Because by the main theorem of algebra, any univariate polynomial of degree at most d has at most d roots. So once you have sampled d minus 1 roots, d plus 1 roots, then the answer of this test is actually deterministically correct, right? So if you evaluate a polynomial of degree at most d, at d plus 1 roots, at d plus 1 different arguments, and if all of them turn out to be 0, then this must be the zero polynomial. So you could replace this black box polynomial test from, instead of sampling arguments x from the set D, just take d plus 1 different values from the set D. Then this is a deterministic test. Right, because any univariate polynomial of degree d can have at most d roots, as is seen in this example, a polynomial of degree 6. But this is not true in the multivariate case, right? So in the multivariate case, this is a simple polynomial of degree 2, but it has more than 2 roots, many more. Actually, it has infinitely many roots, namely all the points on the unit circle are the roots of this polynomial, right? And there are infinitely many points on the unit circle. On the other hand, if you sample any point on the plane, right? Let's say this point, take a random point from the plane, then it's very unlikely that this point lies on the unit circle. So the generic black box test in this special case will still give the right answer with very high probability, actually with probability 1. Let's say that again. Our generic black box test, even in this case where we have a bivariate polynomial, will give the correct answer with probability 1, because the test will only give the wrong answer if the sampled argument x happens to lie on the unit circle, and this happens with probability 0 because the unit circle has measure 0 in the plane, let's say in the unit square of the plane. So that suggests that we should be able to maybe also treat other multivariate polynomials. So this is only one special case, right? Here I've kind of cheated, right? So our situation in this game is that I have an unknown polynomial, but here I've told you the polynomials. Then it's easy for you to check that this is not a zero polynomial, right? You don't need a black box test. So our hope is that even if you don't know the polynomial, if I only tell you it's a n-variate polynomial, n variables, and it has degree at most d, then you can, then the generic randomized black box test still gives the right answer with high probability. So, and our goal will be to analyze that probability, because that's what the whole course CS500 is about, right? And before proceeding, let us recall what is the degree of a multivariate polynomial. There are actually two popular notions of a degree of a multivariate polynomial. One that takes the maximum degree of all variables, and the other that adds the degrees of all variables. And we're going to use the latter. This is called the total degree. So instead of a formal definition, let's just look at the monomial x squared times y to the third. And the maximum degree of this polynomial is 3, because the variable y occurs with degree 3 and the variable x occurs only with degree 2. But this is not the kind of degree we're interested in. We're interested in the total degree. And the total degree of this polynomial is 5, namely add the degrees of the individual variables for this monomial. Do that for every possible monomial in the occurring, and then take the maximum of all these degrees, total degrees of the individual monomials. So that's the notion of a total degree, and we're going to analyze the error probability of this generic black box polynomial test in dependence on n, the number of variables, and the total degree d. Okay, so let's pause here for a minute and give you the opportunity to ask questions before we proceed. Do you have questions regarding error amplification, regarding primality testing, Miller-Rabin, or regarding the problem black box polynomial test that we're going to analyze now, the generic black box polynomial test? Ah, yes, there's a question by Gang Hyunu. Ah, yes, so why is the probability of x be the product of two large primes given as in the slide? Thank you. Let's return to that. Right. So let's suppose that x is the product of two primes. That's a hypothesis, right? So we want to analyze the error probability of our naive algorithm. And we want to bound that probability for all x in the worst case of x, right? That's the point. We're not performing here an average case analysis. This is maybe a source of easy confusion. Average case analysis versus expected case analysis. So we're talking here about randomized algorithm. So that means for any given x, the algorithm, when executed once and again, could give a different answer, right? For the same input x, because the algorithm performs some internal coin flips. And when we analyze the error probability, it means we take any possible input x. In particular, we consider the worst case input x. So this is a expected case analysis is in a sense a worst case analysis, and the expected analysis refers to the internal coin flips. Worst case over all possible inputs x. And this is easy to confuse with average case analysis. So let me use this great opportunity to prevent that confusion. In average case analysis, the argument x is chosen at random. So the input is random, but the algorithm is deterministic. Whereas here, we're talking about the case where the input is the worst case and the algorithm itself performs randomization. We're interested in the behavior of the algorithm with respect to this internal randomization. Okay, so average means x is kind of chosen, the argument x is chosen randomly, whereas expected case analysis means the internal coin flips of the algorithm are random, but the argument is given in the worst case. We're interested in worst case arguments. And the worst case here is indeed when x is the factor of two primes. That's the worst case here. And we're analyzing this worst case, and we're analyzing the probability of our naive algorithm to make an error in this worst case. And in this worst case, the algorithm makes an error unless it guesses one of the two large primes, right? If the algorithm guesses any other number and checks whether any other number is a divisor of x, then it's not, right? If X is the product of two large primes, that means only these two large primes are the only divisors and any other number is not. So when the naive algorithm guesses any other number, it will realize that this number it has guessed is not a divisor of X, and therefore it will erroneously say that X is a prime number because it has not found a proper factor. So put differently, the probability for the algorithm to give the correct answer is only occurs when the algorithm guesses one of the two large primes, and that's very unlikely because there are so many other numbers that the algorithm could guess. Okay, thanks for the question and thanks for the opportunity to clarify about the important but subtle difference between expected case analysis and average case analysis of algorithms. Okay, and now we resume our discussion of the black box polynomial test. And one important question is why are we interested in checking whether polynomial is zero? Let's consider another problem. Let's consider two polynomials and we want to find out whether two polynomials agree or not. Okay, so I have one polynomial p in my right hand and another polynomial q in my left hand, and you're supposed to find out whether these two polynomials are the same or not. And this problem can also be, of course, approached with an identity test, the equality test, namely to check whether these polynomials are the same or not. We take the difference between the two polynomials. So I will convert these two polynomials into one polynomial, namely the difference of the two polynomials. So now by checking whether the difference of the two polynomials is the zero polynomial, that's the same as checking whether the two polynomials agree. So the polynomial identity test covers also the case, the more general, seemingly more general case of whether two given polynomials agree or not. So that's why this is an important primitive for many more advanced computational problems. And we're looking at this generic test, guess a sample argument, and check whether the hidden polynomial is zero on this example argument or is non-zero. And in order to analyze the probability for this generic algorithm to succeed or to fail, to make an error, right? It's a one-sided error in any case, but the probability of this error is analyzed based on the famous Schwartz-Zippel Lemma. So this lemma was, yes, it was discovered by Schwartz and by Zippel independently, but actually it was already discovered earlier, only it was not credited at that time by de Miller and Richard Lipton. And the lemma has the following claim. So it's a purely mathematical lemma, and this is another illustration of a general topic in algorithm design and analysis, namely that it is mathematical observations, mathematical insights that are the key to both efficient algorithms and to the analysis of algorithms. So mathematics is really crucial in computer science with the emphasis on science. So remember when we talked about the Miller-Rabin test, that was also based on a purely mathematical theorem in number theory. And based on that theorem, the test was very simple, both to state, to program, and to analyze. And the same applies here. Once we have established the Schwartz-Zippel lemma, a purely mathematical lemma about probabilities, then it's straightforward immediately to analyze the error probability of the black box polynomial identity test. So what does the lemma say? It says, suppose we have an n-variate polynomial, right? A polynomial in n variable with coefficient, let's say complex number. If you have only real number coefficients, or if you have only rational number coefficients, or even only integer coefficients, that's of course even better. But we try to state it as general as possible. A non-zero polynomial in n variables of total degree at most d. Remember total degree? Right, that's the sum of the exponents occurring in the monomials. And the lemma says, if we sample arguments independently at random from any set S, fixed set S, then the probability for when evaluating this non-zero polynomial at these arguments, the probability to result in the value 0, although it's a non-zero polynomial, this probability is at most d divided by the cardinality of S. Okay, so that means this is a bound on the probability for the generic Blackbox test to fail, right? I mean, this is exactly what it means to fail. I have a non-zero polynomial. You guess arguments, evaluate the polynomial into these arguments, and the result is 0. The result is a root, although it's not a zero polynomial. In this case, this is precisely the case where the generic test provides a wrong answer, one-sided wrong test, a false positive, claiming that this is the zero polynomial, although it's not. And the theorem says this error probability is bounded by d, total degree, divided by S. So let's briefly review this claim before we proceed to prove it. So how can we reduce the error probability of our generic test? How can we make this small? Well, obviously this becomes large if the total degree increases, right? So polynomials with large degree are harder to identify, to detect. That's kind of expected, right? Large degree has more degrees of freedom, so it's there. These polynomials will be more difficult to handle. On the other hand, if the sample set S is large, then that means we divide by a large number. That makes the right-hand side here small, right? So small right-hand side, that means small error probability. So one way of reducing the error probability, one way of increasing, amplifying the reliability of this generic Blackbox test is by using a large sample set S, right? But that's not the most efficient way, right? Maybe if we make the sample set twice as large, that means the error probability becomes twice as small, right? Halving the error probability. If we want to arrive at our bar error probability to 2 to the minus 100, right? That means we should choose a sample set of size 2 to the 100 times d, right? And that's a huge set, right? A sample set of size 2 to the 100. Does it make sense? This is impractical, making the sample set that large. That's completely unreasonable. So what are we going to do instead in order to improve the reliability of a generic Blackbox algorithm? Instead, we're going to choose a sample set of size 2 times d. Why is that good? Well, if you choose a sample set of size 2 times d, that means the right-hand side here will become 1 over 2, right? 1 over 2. And 1 over 2, Then we apply our probability amplification, right? Then we run the same test 100 times. So one execution of the test has error probability 50%. Repeating the test 100 times, then we're at error probability 2 to the minus 100, right? That was the probability amplification lemma. And then we're at probability 2 to the minus 100. That's our bar. That means this algorithm is as good as any, in practical, as good as any deterministic algorithm. So instead of increasing the sample set size to 2 to the 100, which is unreasonable, it is much more reasonable and easy to choose a small sample set of size 2 times d, right? And then repeat the test 100 times. This achieves the same goal, but with much less complexity. Okay. So that's a message to take from the Schwartz-Zippel lemma. It suffices to take a sample set of size 2 times d to get error probability 50%, and then repeat that to amplify to get to error probability 2 to the minus 100. There's one more thing I would like to emphasize, namely, in our original generic test, let's return to that, we would just sample one argument from a fixed set D. So if we have a multivariate polynomial, n-variate polynomial, this means sampling one n-tuple argument, right? If P is an n-variate polynomial, then the argument should be an n-variate vector, right? So in this example, for instance, we would sample a tuple. One point in the plane here means a tuple x, y. But the Schwartz-Zippel lemma takes a slightly restricted approach, namely, we're not sampling one n-tuple, but we're sampling individually the components of this n-tuple. We're sampling x1 from S, then we're sampling x2 from the same set S. So S is actually a one-dimensional set, and we're sampling individual components of this vector individually from this set, independently and uniformly at random. Okay, good. So that's a claim of the Schwartz-Zippel lemma. And now we're ready to proceed to the proof of the Schwartz-Zippel lemma. And the reason of the Schwartz-Zippel lemma is so famous is because its proof is so elegant and simple and easy to understand. Another thing why the Schwartz-Zippel lemma is so famous is because what the right-hand side does not depend on. So here the right-hand side depends on the size of the sample, which is reasonable, right? Larger sample sets give smaller probability. It depends on the degree of the polynomial, which is also reasonable. A higher degree gives higher error probability, but it does not depend on the number of variables n, right? So the left-hand side involves n, how many variables are involved, but the right-hand side does not involve n, which is quite surprising if you think about it. And that's part of the elegance of this Schwartz-Zippel lemma. It does not depend on n. And here it's crucial that we're talking about total degree. If we're talking about maximum degree, then the Schwartz-Zippel lemma becomes more ugly, to say that. Okay, that said, let's proceed to prove the Schwartz-Zippel lemma, and we're going to prove that by induction on n. Okay. Induction start is when n is equal to 1. So let's consider the case n equals 1, the case of a univariate polynomial, where we already talked about the univariate case, where we had this important tool, the fundamental theorem of algebra, at our disposition, right? So fundamental theorem of algebra says any univariate polynomial of degree d, which now agrees with the total degree, right, degree and total degree is the same for univariate polynomial. Any univariate polynomial of degree d has at most d roots. So put differently, if we sample a set, sample a point, 1 point, right? N equals 1 is our case. From this set, what is the probability that we hit a root? That's the case where our algorithm gives the wrong answer. Well, that's the probability, classical probability definition, number of good cases divided by the total number of cases. Total number of cases is cardinality of S, and number of good cases, well, actually number of bad cases. So roots, when we sample a root, that's a bad case. That's the case when our algorithm makes an error. That's the number of roots. And by the fundamental theorem of algebra, polynomial of degree d has at most d roots. So indeed, in this univariate case, this is just the fundamental theorem of algebra. So one way of looking at Schwartz-Zippel Lemma is as a generalization of the fundamental theorem of algebra, not speaking in terms of the number of roots, which will become infinite already in 2 variables, but in terms of the probability of hitting a root. So because the univariate case n equals 1, that's just the same as the fundamental theorem of algebra. That covers our induction start, and now we proceed to the induction step using the induction hypothesis. So now we consider the n-variate case and suppose that for n minus 1 variate polynomials, this inequality already holds. And for this induction step, the following probability estimate will be helpful. So let A be any event, then the probability of A is equal to the probability for A and B plus the probability of A and not B, where B is any other event. So this is just kind of decomposing the event A into 2 disjoint events. These events are disjoint, right? These are events where B holds, and these are the events where B does not hold. So this is a decomposition of A into 2 parts, disjoint parts where B holds and B does not hold. Therefore, their sum is equal to the total probability of A. So that's easy, right? And now we're going to bound to estimate further this expression, namely the probability for A and B to happen is, of course, at most the probability for only B to happen, right? Because this event is a subset of this event. Therefore, by monotonicity, the probability for this to happen is less or equal to the probability for this to happen. Okay. Now let's look at the next term. The probability for A and not B to happen, that is equal actually to the probability, to the conditional probability times the probability of not B, right? So that's, as you have recalled the definition of conditional probability, this is exactly the definition of conditional probability. If you take the conditional probability of A with respect to not B, multiplied with the probability of not B, that is by very definition the probability here. And now we're going to apply another estimate, namely we're going to drop that part by observing that this probability is of course at most 1. Any probability is at most 1. So by canceling this part, we only increase the probability. So that's justifying this inequality. Put differently, there are 2 reasons for this inequality. First, because this probability is less or equal to this probability. And secondly, because this probability is equal to the whole expression, which is less or equal to only this part of the expression. And then we're going to use this, this bound on probabilities when we now do the induction step of proving the Schwartz-Zippel lemma. Okay, and in the induction step, we write the original n-variate polynomial, right? Non-zero n-variate polynomial as a univariate polynomial in the last variable. So xn is the last variable. And we have several powers of xn here. And the coefficients, well, in general, the coefficients are numbers, but since we have a multivariate polynomial at our hand, the coefficients themselves are again polynomials, namely polynomials in the other variables. So that's one way of looking at a univariate polynomial. A univariate polynomial is the same as a univariate polynomial, but its coefficients are in turn polynomials in the remaining variables. So that's only what we do for the purpose of analysis here. And now we can apply the induction hypothesis, because induction hypothesis applies to n-1 variate polynomials, right? So in order to do this, let's consider J, one of the exponents occurring in this decomposition. J such that this coefficient, which is a polynomial, an n-1 variate polynomial, is not a zero polynomial. Such an index exists. Why? Because our original polynomial is supposed to be not the zero polynomial. So when we write on this polynomial, that means not all coefficients are zero. Otherwise, the entire polynomial would be the zero polynomial. So there exists such a J, possibly several J, such that this coefficient is not the zero polynomial. And we're going to take the maximal such index J. But differently, we take the maximum exponent here in this decomposition where the coefficient is non-zero. This is what we would usually call the degree of a univariate polynomial, the maximum J, such that the coefficient to J is non-zero, right? That's our degree in the univariate case, okay? So, and for the purpose of analysis, we're going to look at this J and then try to estimate the probability for the randomly chosen, independently, uniformly at randomly chosen x1 to xn to evaluate, make this entire polynomial evaluate to zero. And we're going to do that using this probability expression. Namely, we're going to choose as A, let me first write it down. We're going to choose as A, no, we're going to choose as B, the probability that the J's coefficient here, n-1 variate polynomial, evaluates to zero on our sample. That's the event B here. And what is this? This is so A should be this event, the probability that our original polynomial evaluates to zero on the given sample. And B is this event, the event that the J's coefficient polynomial evaluates to zero on our sample. And then, according to this inequality, we need to consider here the probability of A conditional to the probability of B. That means the probability of our original polynomial to evaluate to zero conditional to the probability that the J's coefficient polynomial does not evaluate to zero, right? That's why it says not B. Okay, so this inequality is exactly what an application of this general estimate on probabilities. And now we're in business. Now we can conclude the induction step because this is a n-1 variate polynomial, and we know its degree. Namely, what is the degree of Pj as an n-1 variate polynomial? Well, since our original polynomial has degree d, this monomial has degree j. That means, since we're talking about total degree, this monomial has degree d minus j, right? So remember, total degree means adding the degrees of these individual monomials. This monomial contributes degree j. The whole polynomial has degree at d. Therefore, this polynomial has degree d minus j. And now our induction hypothesis says the probability for this polynomial of degree d minus j to be 0 is at most d minus j divided by s. Yes, exactly this. This is the induction hypothesis. Let me say it again. Our original polynomial has degree d. That means this expression, this product has degree d. This already contributes degree j. Therefore, this must have degree at most d minus j. And for this n minus 1 polynomial, the induction hypothesis applies and says that the probability for this n minus 1 polynomial of degree d minus j to be 0 is at most d minus j divided by the set of the size of the sample set. Okay, first part. Now about this expression. What is this probability? This is a probability that we have this. Now this is a univariate polynomial. Let me emphasize that. So we've sampled already x1, x2, x3, and up to xn minus 1. We've plugged these values into the polynomial pj and arrived at a non-zero value. That's what the conditional probability says. This condition holds, which means this part evaluates to non-zero. So that this has already become, this polynomial has boiled down to a number because we've already plugged in values for the first n minus 1 variables. That means that the rest is just a univariate polynomial of degree, well, of degree j, right? We're looking at this whole polynomial. This polynomial is supposed to have degree d, and all larger coefficients, all coefficients beyond j are 0, because that's why we chose j maximal, right? So all pj minus j plus 1, pj plus 2, up to pd are 0. Therefore, this univariate polynomial has degree j. And now we apply the induction hypothesis again for the univariate polynomial of degree j. To evaluate to 0, this probability is j divided by the size of the sample set, univariate case. So then adding these two probabilities, that gives exactly the claim, right? D minus j divided by the set of the sample set plus j divided by the sample set size, that's d divided by the sample set size. And that concludes the induction step of our proof of the Schwartz-Zippel Lemma. And yes, time is up. So we will resume next week by applying this Schwartz-Zippel Lemma, by applying this polynomial identity test, randomized identity test, in order to arrive at a very simple algorithm for solving the perfect matching problem on graphs. That's all for today. Thanks for joining, thanks for your attention, and see you next